Hi students, in this class we see important aspects of electric field. What is the nature of electric field? How we can write Coulomb's law in terms of electric field. Those things we see. So first thing we have to know is electric force. The force on a positive charged object is in the same direction as the electric field at that point. That means what they are telling, the force on a positive charge is in the same direction as electric field. That means for positive charge, force and the electric field are in the same direction. Why? We know that E is equal to F by Q, right? So this implies F is equal to QE. Clear or not? So for positive charge, Q is positive. So this is just a number, scalar. So vector multiplied by scalar, it is a vector only. So this will be a number, a vector. So that is positive vector, right? So force is some positive vector. So both are having the same direction. Force and the electric field are having the same direction for positive charge. That's why you see force is going in this direction. Electric field also, F is in this direction. E is also pointing towards the same direction. So E and F, both F and E, both are vectors, are in the same direction for positive charge. Suppose, right here you see it's going like this. E is electric field, green lines, F is a force, both are in the same direction. Suppose if charge is negative, what happens? F is equal to minus Q, because Q is negative, minus QE. So here force and field are in some negative E, that E, some constant, so negative E, right? So force and field are in opposite direction. This minus indicates opposite, right? So here you see for a negative charge, E is going in this direction and F is going in this direction. That is, both are opposite to each other. Here also you see electric field is going in this direction outward and a force is coming opposite to the electric field. So for positive charge, E and F are in same direction. For negative charge, right, if E goes in this direction, F will go in this direction, right? That is the first thing we must remember. Next one, you see for positive charge, electric field points radially away from the source. So this is positive charge, it will go radially away, right? Similarly for negative charge, it is go radially inwards. For example, for positive charge, it will be going like this, go away, radial. This is called radially. It is spreading like a sunlight. It is radially away. For negative charge, it is going radially in. Electric field is going, these blue lines are electric field lines. This is going inside. This is known as radially towards the charge. For positive charge, electric field radially goes away. For negative charge, they radially goes towards the charge, right? Next one is very important. The force experienced by discharge at point P with electric field, we know. Yes or no? So that is given by E is equal to F by Q. So F is equal to QE. Just now only I told. What is F? Coulomb's force. What is E? Electric field. So this equation F is equal to QE expresses Coulomb force in terms of electric field. So this is very important relation. F is equal to Q into E. Clear? So that Q is just a number, right? Charge, scalar. So this relates electric field and force. See, very important point is for any mathematical equation, right hand side is cause, left hand side is effect. So what this equation is telling? Electric field causes force. That's what I told in the last session, right? Every charge create field, field will create force, that force will be felt by the discharge, You remember this? So hereafter, whenever you see any equation, just remember right side is a cause, left hand side is the effect. So electric force is created by, electrostatic force is created by charge, electric field. Who is creating electric field? Charge is creating electric field. Very simple. Very, very, very important principle. Clear? Okay. Next. The electric field at point P is the force felt by a test charge. We know that, right? Just now only in the last video we have seen that. Is it okay? So, but what is Q, capital Q here? In that example I have kept capital Q is a source, small q is a test charge, electric field is force by test charge, right? We know that force is force between the two charges, K into Q by R squared. This Q is divided by R cap. So what is happening? Q cancel. You see electric field is purely depending on source charge capital Q, right? So electric field is independent of test charge. Very, very important. It depends only on source charge. Clear? So that is another important point to be noted. Electric field is independent of test charge, depends only on source charge. Right? Next thing we have to remember is, we know this equation E is equal to kq by r squared, where k is equal to 1 by 4 by epsilon naught. This equation is only valid for point charge, right? So don't forget. What is point charge? It is the smallest charge whose dimension is small compared to the other dimension involved, right? So for infinite number of charges, we have to go for continuous charge distribution that we will see in the later classes. Okay, sorry. So E is equal to kq by r squared into r cap is applicable only for point charge, this equation. For continuous charge, I will explain, right? Next thing is, when distance increases, electric field decreases in magnitude. You see E is equal to kq by r squared into r cap. What is r? Distance between source charge and field location, or field point, the point at which we have to find the field, right? So when distance increases, what happens? E decreases. So when R increases, E decreases, like force, right? This is another important point, right? Now we see that, for example, here you see, suppose point charge, right? I want to find field here, I want to find field here, I want to find field here. This distance is close, P1. At this point I want to find field, I want to find field. At this point I want to find a field. Where it will be maximum? The field will be maximum at this point, because this point is closer to the charge. So electric field at 1 is greater than electric field at point 2 and electric field at point 3, because point 1 is closer, right? Point 2 is somewhat away, point 3 is more distance, right? So when distance increases, electric field decreases. So that's why what we do when we draw the diagram, you see nearby we will have a line like this, big lines. After that we reduce the length of the line. Length indicates the magnitude of the electric field. So when distance increases, the electric field magnitude is decreasing. So like that we put this plus, because electric field goes out for positive charge, then it's going, then it's reduced, like that we have to draw, right? Here similarly here it's going like this, then reduce. So when distance increases, electric field magnitude is decreasing, right? This is very, very important point. We have to draw lines like this only. Clear? Okay. So moreover, every point the distance will vary. This point is different distance from this point to this point. So electric field will vary with respect to location. So electric field will vary with respect to location. So every point we will have a different electric field. Okay, that is very important point. Right. Next we see another one important point is we are having two kinds of electric field. One is uniform electric field and another one is non-uniform electric field. What is uniform electric field? As the name itself is telling, the electric field is uniform. That means what? Electric field should have constant magnitude, because electric field is a vector quantity. So it has both magnitude and direction. If magnitude is constant and the same direction is same, then we call that electric field is a uniform electric field. Here you see for all the arrow marks, that is electric field, the length is same. Here. For all arrow marks, the length is same and all arrows are pointing towards the same direction, that is along x-axis. So it is uniform electric field. Suppose if the magnitude is not constant and variable and direction is different, right? Or both magnitude and direction is, if magnitude is not constant and direction is not same, that is also non-uniform electric field. If magnitude is constant but direction is different, that is also non-uniform electric field. If direction is same but magnitude is variable, that is also non-uniform magnetic field. See, just now only I have drawn this. Here you see the length is wide, then it is reducing, then it is reducing. So here magnitude is changing. Direction is same, but magnitude is changing. So it is a non-uniform electric field. Okay. So here you see for point charge, the magnetic field, electric field will be like this. So it is non-uniform in nature. Very important point. Right? Why magnitude is going like this? That's what we have told. When distance increases, the length of the magnitude of the electric field will decrease. This is electric field due to point charge equation. Because we have taken only source charge and test charge. The test charge is a point charge. This is the equation for E due to point charge. They may ask in exam, what is the electric field due to point charge? Why it is called electric field due to point charge? We found E is equal to F by Q, where Q is a test charge which is nothing but a point charge. So capital Q is also point charge. So E is equal to KQ by R squared into R cap is the electric field due to point charge. When R increases, E decreases. That's what this shows. Right? So when our distance increases, the magnitude is decreased. Clear? So that's why electric field due to point charge is non-uniform in nature. Right? So that's all about this session. Hope you understand everything very clearly. If you are having any doubt, please ask me in comment section. I will clarify all your doubts. Thank you.